All right, so our goal today is to talk about Polya counting. So this actually is going to harken back to a question that we talked about a long time ago. So let's remember a question that we did a couple months ago. So that question was about counting necklaces of colored beads. So by a necklace of colored beads, remember that I'm thinking something like this, where some of these are, in this case, some of them are black, some of them are white. Okay, and so we did this question, and so you might at first be inclined to say, okay, well, there's going to be 2 to the 5th, because this bead can be black or white, this bead can be black or white, this bead can be black or white, and so on. But then you realize there's this rotational symmetry here. So then you might be inclined to say, okay, so the number is 2 to the 5th over 5, but that can't possibly be right because this number isn't an integer. Well, that's a problem. Okay. But why is this number wrong? Well, this number is wrong because there's 2 special necklaces, namely the all-white one and the all-black one, which don't vary by the rotational symmetry. So we need to separately count the monochromatic and the dichromatic necklaces. And so when we go to count the monochromatic ones, well, there's just 2, the one that's all black, the one that's all white. Okay. When we go to count the dichromatic ones, then I'm going to go ahead and say, okay, well, there would be 2 to the 5th minus 2 ways to color this in a way that is 2 colors, but then we have to divide by the fact that there's 5 rotations. Okay. And so in total, that will end up giving us 6. So the total number of necklaces we find out is 8. Okay, not so bad. All right, so homework question for you that you can go ahead and tech up. What if I allow myself also to use red beads and blue beads? Okay. So that is to say, how many necklaces can I make with 4 colors of beads? Okay, still length 5. All right. But you might recall we next thought about a question that looked something like this, which is a very innocuous looking question. We just answered the question, how many necklaces can we make with 5 white or black beads? Let's do it for 6. How much harder can it be? And it turns out the answer is, well, it's actually quite a bit harder. Right? And here's why. Namely, when I go to write down necklaces with 6 beads, they end up looking something like this. Okay. And you might again try the same thing. You might try and count monochromatic ones, of which there are still 2, and then try to count dichromatic ones. Okay. And so you might figure, oh, well, that's going to be 2 to the 6th minus 2 divided by 6, but a little calculation tells you that is 62 divided by 6, which would say that there are 5.2, or sorry, 10.3 of them. Okay, so that's not right. And what went wrong? Here's what went wrong. When we did this before, the key thing that made our method here work was this dividing by 5, which worked because as soon as we knew there were 2 colors of bead or more than 2 colors of bead, then we knew that every one of the 5 rotations of our necklace were going to be different, which then meant, hey, I can just take the total number of necklaces and then divide by the number of symmetries they each have. Okay. This is what we've in the past called sort of freezing the necklace and then dividing by the symmetries. So it might seem to stand to reason that if I do that with this necklace, the same thing will happen. So you might, for example, look at that necklace. And if you go ahead and you look, this necklace has 6 rotations, and they're all different. So this and its 6 rotations, that I should divide by 6. But the trouble that sneaks in here is that if I look at a necklace like this, how many rotations does this necklace have? Well, it doesn't take too much to convince yourself this necklace has only 3 rotations. Okay. And that's because these 2 black beads here, if I rotate 3 times, they switch places with those 2 black beads over there, and vice versa. So with 3 total rotations, I get back where I started. Okay. And so that means when I divided by 6 over here, that I actually only counted this necklace arrangement with a weight of 1/2, meaning I counted this as half a necklace, which doesn't make sense. That's not what I want to be doing. So I have to fix this. Okay. And so that's why this case is more difficult. This case is more difficult because when I look at this 6, I have some necklaces that I am counting 6 times, some necklaces that I'm counting 3 times, some necklaces that I'm counting only 1 time. Those would be the monochromatic ones, and so on. So before we go on, I want you to think about a couple questions. So pause and think about these. Okay. So first question. What is different about the 5-bead question and the 6-bead question that means that it worked over here and it does not work over here? That's the first question. Second question. When we got this 10.3 number here, which we agreed was ridiculous, was that an overcount or an undercount? Right. So in other words, when I'm counting the dichromatic necklaces, we know there aren't 10.3. Are there supposed to be more than 10.3, or are there supposed to be fewer than 10.3? That's the question I'm asking there. Okay. And last question I want to ask, we've said there are some necklaces that get counted 6 different times across the 2 to the 6th ways of coloring this. There are some necklaces that get counted only 1 time, namely the monochromatic ones. And then there's this one, at least, that only gets counted 3 times. Are there any other numbers? That is, can you make a necklace that's counted 2 times, or a necklace that's counted 4 times? And I want you to think about that as well. All right, so I would pause the video here and think about that, and then I'll get to wrapping up this piece. All right, so what is Polya counting? Polya counting, as it's going to turn out, is going to be a theorem that's going to let us answer all of these kinds of questions in a vast degree of generality. Okay. Namely, Polya counting is going to let us answer the question for a structure with nodes and symmetries, how many ways are there to color the nodes in one of m colors that are visually distinct? So our underlying structure in the examples that we just did was the necklace before we colored it. So in the case of 5 beads, this was our underlying structure. And so these 3 things, this is the structure. And then each of these things, these are the nodes that we're going to color in one of 2 colors. Namely, we're going to color them black or color them white. Right. And then what are the symmetries? The symmetries of this necklace, this structure, are these 5 different rotations. That is, not rotating it at all, rotating it once, twice, and so on. Okay. And so our goal here is to understand a theorem that will describe to us exactly how many ways there are to color necklaces with 5, 6, any number of beads you want, and also other things. So for example, we've talked before about coloring the surfaces of cubes, and we'll do some other examples too.